A stirrer is a machine that uses circulatory movements in order to accelerate the heat and mass transfer processes. These devices can be classified according to the direction of the current they generate, in axial flow and radial flow stirrers. The last one produces a movement perpendicular to the direction of the axis of rotation and will be the object of study in this project. Within radial flow stirrers, Russian turbines are the most widely used type of stirrers at an industrial level, and are considered as a reference for the study of turbulent steering processes. Given the importance of the agitation operation in the industry, the objective of this project was to analyze the performance of a Russian turbine stirrer using CFD and to design a new agitation mobile that allows to obtain a higher power number.
The design of the new mobile consists in a flat plate drive without disc, the above because in literature it was found that the Russian drive had a higher power number, so we decided to keep the geometry in the plate but skip the disc. According to literature, as the number of plates increases, the power number increases, so we decided to implement the new impeller with 8 plates. In addition, the upper and lower ring was added to achieve radial and axial flow. The dimension of the plate 8 and the impeller diameter were taken as the maximum load for the project.
And the top interface and slip condition is determined because there are no walls. This condition means that the velocity of the fluid at the boundary is not equal to the one of the boundary. On the walls of the agitator, there is a no-slip condition because a solid boundary exists. This means that the velocity of the fluid at the boundary is 0. The rotation velocity was calculated solving for the Reynolds equation, varying on a Reynolds number logarithmic scale from 1 to 100,000.
For the module selection, it will use water or the liquid, assuming constant density, segregated flow because it solves the equations in a segregated manner. It fits better for incompressible fluids and saves the computational time. The simulations were run using steady and unsteady state. Kappa Omega turbulence model was selected because of its performance in low turbulence areas, and turbulence suppression was selected for laminar flow.
A volumetric meshing was performed to allow an adequate modeling of the system. A polyethyl measure was used considering its robust convergence at lower values and its faster convergence with fewer iterations. A prism layer mesh was used because it's composed of prismatic cells that allows to know the behavior of the fluid in areas close to the walls. Moreover, it's numerically more stable, less diffuse, and more accurate than an equivalent tetrahedral mesh. And finally, a surface remeasure was used in order to improve the quality of the surface as well as to optimize it for the model of the volumetric mesh. Meshes were created for both models using 0.4 mm base size and 3 prismatic layers. A number of 762,860 cells was obtained for the Russian model and for the new 800,067 cells.
The Y plus values obtained are kept in a range that indicates what function is modeled correctly. For the simulation made with Reynolds number of 100,000, values between 5 and 27 were obtained. This means that the mesh used is not fine enough for a thermal region, but it adapts to laminar and transition regions. Furthermore, these values indicate that the mesh is sensitive when the fluid begins to develop, so error in boundary layer in turbulent region increases. The Y plus values for the new impeller increases with respect to Ruston, so the results obtained in this simulation are less accurate. It is also observed that the values obtained with unsteady model are above the values obtained with a steady model, since the latter does not consider changing time of other design variable that is thus considered the first model.
The velocity results for the Rushton and the new mobile can be seen on the figures below. According to them, the velocity on the new mobile reaches higher values. The range of velocity values corresponds to the one reported in literature that goes from 3 to 7 meters per second. The velocity increase in the new impeller can be due to the higher number of blades on the mobile. From the streamlines animations, it can be noticed a radial flow as expected. According to literature, this type of flow provides a high tangential speed but decreases the drive capacity.
The results of the turbulent kinetic energy present bigger values for the modified impeller in comparison with the Rushton for some Reynolds numbers. This value depends on the velocity, so if the velocity report increases, this report will increase too. This implies that there is more dissipation of energy and an increase in turbulence.
Regarding the figure shown above, it can be noticed that there is a direct relation between the power consumed by the stirrer and the Reynolds number. As the velocity increased, the Reynolds number showed a higher value, and in the same way, they were required for the impeller to achieve that velocity increase. When comparing the curve for the new mobile and the original one, it can be concluded that due to the geometry of the new mobile, the power consumed in order to reach the same velocity is greater than the one consumed by the original turbine. This responds to the fact that the new impeller was designed with more blade in order to increase the power number. In terms of the results obtained for the torque, it can be said that the behavior which increases as the Reynolds number increases is similar to the behavior found in literature, considering that for a higher velocity, the force needed in order to make the axis of the impeller rotate will be greater. In compliance with the proposed objective, when observing the behavior of the shear rate, it is possible to notice that the velocity gradient generated by the new mobile is greater than the one generated by the Rushton turbine, meaning that with the new mobile, the layers of the fluid move faster.
Now, regarding the power number, as it is observed in the graph for the Rushton mobile in a steady state, a different behavior was obtained to the one calculated with the literature because a difference in level is observed in their transition zones, which could have been given by regions where obstacles are formed for the passage of the fluid, generating instability in the power number. Nevertheless, in the turbulent regime, similar behavior are observed between the curve because for the Rushton mobile in these zones the power number begins to stabilize. In addition, for the Rushton mobile in steady state, similar results were obtained to those calculated with the literature, since the power number obtained are close and the curve has decreased behavior until it stabilizes. Also, the errors were calculated for the NP obtained in a steady and unsteady state, and it's evident that the results are not far from the literature, although they were higher for the simulated Rushton in an steady state. It's important to clarify that since negative values were obtained, the RMS was used in order to calculate an average between the NP values and that determined the errors. On the other hand, a regression was performed to determine the two equations that allow representing the NP curve for the results obtained with the new mobile in a steady and in a steady state. As can be seen in the equation, the behavior of the two curves is similar, since the coefficients obtained are within the same order of magnitude. However, the results are not completely stabilized, so it's not possible to evidence a stable behavior for the power number. Finally, considering the result obtained for the power number of the two mobiles, it can be concluded that in both the state steady and unsteady, for the new design, high values of NP are reached than with the Rushton mobile. However, as it observed in the graphic, in the unsteady state, both curves maintain a very similar behavior, while in a steady state, the Rushton mobile is closer to the results obtained in literature.
The deviations of the power number results from literature could be due to lack of time and iterations in the simulation. As it can be seen in the figures, the power number results do not converge for low Reynolds, but oscillate between a wide range of values.
From the results obtained, we conclude that the simulations performed in the steady state have less error with respect to literature than the results in the unsteady state. The literature is surely reported in the steady state.
The results obtained for low Reynolds numbers were not taken into account because they don't have a physical meaning due to its minimal value of torque.
Taking into account the results, it is possible to conclude that the objective of the project was fulfilled, since it was possible to design a new agitation mobile that allows to obtain a higher power number than the Rushton turbine. However, this turns out to be inconsistent with literature, since the Rushton turbine gives values for the power number between 5.5 and 6, while the model used to carry out the design of the new impeller, the Jacobi, only reaches values between 4.5 and 5.